Hi and welcome to this lesson on total entropy changes. In the last lesson, I introduced entropy. So we had a look at what it means, the fact that it's the overall measure of the disorder of a system, and it depends on the state of matter, the number of particles, and dissolving. So we learned that it can be calculated by subtracting total enthalpy of reactants, the total entropy of reactants from the total entropy of our products. You can see how easy it is to get confused between entropy and enthalpy, so be really, really careful when you're writing answers for this. They mean very different things. So in this question, we're going to have a look at how to calculate the entropy of the surroundings and then work out the total entropy change. Key terms that are quite useful here, of course, the system. So understanding what the system is and understanding what we mean when we say the surroundings, because they're quite vague terms by themselves. When we talk about the system, what we mean is we're referring to the reactants and the products under investigation in that chemical reaction. When we talk about the surroundings, we're thinking about everything else. Anything else that isn't the products and the reactants in that particular reaction under investigation. So examples of things that are in the surroundings would be the solvent, also the air around the container itself, and anything that's dipped into the reaction mixture. None of those things are actually the reactants and products that are under investigation, so they all come under this topic of the surroundings. We care about the entropy of the surroundings. It's actually really important because during a chemical reaction, energy is transferred between the system and the surroundings. It's either taken in or it's given out. And we've learnt that during the topics on enthalpy. So that's given off as heat or taken in. As a result, the entropy of both the system and the surroundings gets altered, and we need to be able to assess how much that gets altered and get a numerical value. An example here, in exothermic reactions, energy gets transferred to the surroundings. And in those cases, entropy is likely to increase. And conversely, in endothermic reactions, energy gets absorbed from the surroundings into the system, and the entropy is likely to decrease. In order to calculate a numerical value for the entropy change of the surroundings, we can do minus the enthalpy change divided by the temperature. You need to be really careful here because this minus sign is very important. So if the reaction is exothermic and the enthalpy change is negative, then negative of a negative means it's actually going to be a positive enthalpy change in that particular case. Using the entropy change of the surroundings that we just learnt how to work out and using the entropy change of the system that we worked out how in last lesson, we can work out the total entropy change. And that gives us an idea of the feasibility of a reaction, so it's a really important number. Let's have a go at a question to work this out. You'll have noticed there that enthalpies are measured in kilojoules, but entropies have to be in joules. So I needed to convert my enthalpy value that's in kilojoules per mole into joules per mole. So I times the value by 1000. Why do we calculate the total entropy of the system? Well, we care about reaction feasibility. So feasible reaction is a reaction that's likely to occur when the reactants are mixed and the activation energy isn't getting in the way. Many exothermic reactions they'll occur spontaneously, so they're feasible because they do not require an external source of energy to get going. That means that a negative enthalpy value or an exothermic reaction, they're more likely to be feasible. And we can see it's a factor that contributes as to whether a reaction happens on its own accord. Linking this to entropy, reactions with a positive entropy of the system are more feasible. And this is because the natural movement of a system is towards a state of greater stability. So this is greater entropy as we discussed in the previous lesson. However, it's not always the case. For a reaction to be feasible, the total entropy change needs to be positive. And that is why we're learning how to calculate that value. Total entropy change takes into account the role played by enthalpy, by temperature, and also kinetics and all these come together to determine whether a reaction occurs or not. If any of these factors change, so will the overall entropy value, and hence the feasibility of the reaction. Let's have a look at an example question.